Good afternoon. My name's Groh, and I'm supervised by Professor Paul Weaver, and I'll be giving a brief overview of some of my work on the mass optimization of variable stiffness wing panels. I'll skip the outline because I'm the only one here that has one. So research into optimizing the structural performance of composite laminates by spatially varying the fiber orientation over the planform has been going on since the 1970s. The basic premise for this is that by varying the fiber orientations over the plate, or the structure in fact, we can dramatically increase the design space available for tailoring the structural performance to a specific application. For example, researchers have shown that we can reduce stress concentrations around holes by aligning the fiber paths with the directions of principal stress. Another area of improvement that we've been working on here at the University of Bristol is improving the buckling and post-buckling performance. And in fact, we can more than double the buckling performance of the critical buckling load of a flat panel. The basic mechanism that is behind this behavior is that by spatially varying the fiber orientations, we can remove load from unsupported areas towards the center of a panel where a buckle wave form would occur and redirect it towards stiffened edges where there are support conditions. Another possibility is that the manufacturing techniques opens up is that we can facilitate smooth transitions between areas with different layout requirements. For example, in trees, there's a smooth transitions of the fibers from the trunk leading into the branch, and we could apply this concept, for example, trying to have fibers go smoothly transition from a fuselage straight into a wing. Traditionally, these variable stiffness composites are manufactured using the advanced fiber placement process, and basically what researchers have done is tried to use a developed manufacturing technique and bootstrap the variable stiffness capability to these machines. One of the problems with the AFP process is that because toes are bent in plane, we can get toe buckling on the inside radii and toe liftoff on the outside. Furthermore, if we're going to cover a whole planform, a whole area of a plate, we require gaps or overlaps to cover the whole planform. To minimize these manufacturing defects, at the University of Bristol, we've developed the continuous toe shearing technique, CTS, which shears the toes at the point of application to steer the fibers. Another advantage of this technique is that individual fiber paths can be tessellated to cover the whole planform without any gaps or overlaps. Another feature of the CTS process is that the thickness of a toe and the steering angle are coupled, which means that we get this thickness variation across a panel. And the thickness variation can be quite large. So for example, at the panel center, we could have a normalized thickness of 1, and it could be 3 times that towards the edges. And we have shown that this asymmetric thickness profile makes the structure behave more in a shell-like manner, which means that the membrane and the bending behaviors are coupled, and we can use this to further tailor the buckling performance, and in fact also the post-buckling performance. So I've looked at a simple optimization study of an aircraft wing skin panel, basically a panel in between ribs and stiffeners under uniform end compression of 250 kilonewtons. The panel is square, 250 millimeters in dimensions, which means that the load is about 1 kilonewtons per millimeter, which is a classic load case for such a wing panel. And I've attempted to optimize the stacking sequence, which is still balanced and symmetric, and follows manufacturing constraints of the CTS manufacturing process. And no buckling and static failure is allowed to occur, where the static failure criterion is basically the maximum Tsai-Wu failure criterion throughout the laminate. I've implemented an analytical model in MATLAB and used the in-house, the MATLAB genetic algorithm technique to optimize the structure. The results that we see, if you look at this table, the top line is a straight fiber classic airspace panel. So all the classic lamination guidelines are followed. And the critical buckling load is at 1.13, where anything lower than 1 is failure. And the Tsai-Wu failure criterion is 0.3, where anything above 1 is equal to failure. And the end compression is 2,600 microstrain. And because of this 0.3 Tsai-Wu failure criterion, there's a lot of residual strength left within the panel. And using the toe steering, we can we can bring the buckling factor down to 1 and also nudge up the Taiwu failure criterion to 0.89, which means that the two failure criterion are now closer together. Now the problem is that the compressive microstrain is at 5,500, which is slightly above the classic range between 3,000 and 4,000 that is used for damage tolerance in the aerospace industry. So I've also applied a constraint of 4,000 microstrain, which reduces the weight savings from initially 30%, so a third of the weight is shaved off, to about 21%. And the reason why this occurs is that buckling is driven by local stiffness variation. So we want to have high stiffness at the edges and less stiffness at the middle of the panel so that loads are redistributed to the supported edges. But the overall compressive strain is governed by the global stiffness. So if there's a weak link, a weak member somewhere, that is going to deform more, and we get higher strains. So in order to further improve the performance of these panels, I guess damage tolerance models would have to be incorporated so that we can maybe move up from 4,000 microstrain to 5,500 microstrain limits within the industry. Another added effect that I didn't optimize, but that came out of the results, is that the post-buckling stiffness of our two toe-steered optimized results is actually higher than that of the straight fiber design. So classically, upon buckling, the stiffness of a quasi-isotropic laminate is halved in the post-buckling regime, and these two toe-steered designs actually have residual stiffness of 80%. So there's a significant increase in the post-buckling stiffness, which opens up possibilities for using the nonlinear regime in the future. So to conclude, I've presented two optimized CTS designs where the best design reduced the mass of this aircraft panel by about a third compared to quasi-isotropic laminates, and further reductions are dependent on this maximum strain limit. Also, the post-buckling stiffness may be improved at the same time, and in the future, I'm coming towards the end of my PhD, but in future, there's room for experimental validation. Thank you. I'd like to acknowledge my sponsors, the EPSRC, and if you'd like to, I don't have a video game downstairs, but if you'd like more information about the topic, there's also a conference paper available online. Thank you.